Welcome to the Sargan lecture, which will be given by Guido Imbens in a bit. The Sargan lecture has a long history at the Royal Economic Society, and since 2019, it is sponsored and published by the Econometrics journal under a new remit, which reads that it commemorates the fundamental contributions to and profound influence on econometrics by John Dennis Sargan, and that it does so by promoting econometric theory and methods with substantive, direct or potential value in applications and their actual empirical application, which nicely coincides with the editorial aims of the Econometrics journal. Now, the inaugural lecture under this new remit was delivered by Jim Heckman in 2019 and will be published in the May issue of the Econometrics journal, together with the proceedings of a special session on the panel data that we organized at the same conference. There was no lecture last year, unfortunately, but we're very much looking forward to the second lecture in this series, which will be given by Guido. But before that, I first would like to give the floor to co-editor Michael Jensen, who will award and celebrate the 2018 and 2019 Dennis Sargan Econometrics Prizes.
Thank you, Jaap. Greetings from California. So I'm here to award and celebrate the winners of the Sargan Econometrics Prize from 2018 and 2019. As you may know, the Sargan Prize was introduced in 2011 by the Econometrics Journal on behalf of the Royal Economic Society. It's awarded for the best unsolicited article published in our journal, the Econometrics Journal, in any given year. And the one criterion we have is that the winners of the prize have to be within 5 years of being awarded their doctorate. This year, we are awarding not one, but two prizes because of the pandemic. So we're handing out both the 2018 prize and the 2019 prize. The 2018 prize goes to Matt Goldman and David Kaplan. David is here today. And they're getting the prize for their article, Nonparametric Inference on Conditional Quantile Differences and Interquartile Ranges using L statistics. That article was published in the June 2018 issue of our journal. The 2019 prize is awarded to Arturas Joris for joint work with Joachim Westerlund. The title of that article is Optimal Panel Unit Root Testing with Covariates. It's given only to Arturas because he was the only author who satisfies the criterion of being within 5 years of receiving the doctorate. So this was not meant as a disrespect to Joachim. And this article was published in the January 2019 issue of the journal. I'll say, in the interest of time, I'll just say a couple of things about each paper individually, but for completeness, let me say that, among other things, these both of the prize-winning articles, although they are very different in detail, what they have in common is that they very nicely represent what it is we're trying to achieve with the journal, which in Jaap's words is to publish econometrics that matters. So if you actually pick up these articles and read through them, as I would encourage you to do, I hope you will agree with me that this is exactly the type of econometrics that meets the Goldilocks criterion of having both something for the pure theorists in the audience, but also for consumers of econometric theory as well. So in more detail, the 2018 prize, again, goes to David Kaplan and Matt Goldman for their article, Nonparametric Inference on Conditional Quantile Differences and Interquartile Ranges using L statistics. In a nutshell, what that paper does is it proposes a way of constructing confidence intervals for things such as interquartile ranges, where what is interesting and useful about those confidence intervals is that they are very accurate in a sense that it can be made precise in a way that would satisfy an econometric theorist. So they have that very interesting theoretical property, which also translates into things that practitioners will care about, namely the intervals are as short as can be, subject to covering what you're interested in with a certain pre-specified level of significance. And on top of that, it is also, as it turns out, the method is very easy to implement. So it basically ticks all the boxes that we would want for any article in the journal. In this case, it was also happened to be authored by people who were within 5 years of getting the doctorate. So it was an easy call. We gave the prize 2018 to Matt Goldman and David Kaplan, where David is here today to accept the prize. For 2019, in many ways, the article is similar in a big picture sense to the 2018 winner. The 2019 winner is Optimal Panel Unit Root Testing with covariates. What is at least theoretically interesting about that paper is that it points out what you might call a complementarity between a panel setup and the existence of covariates that arises in connection with unit-root testing. So here, it's been known for a while how to make good use of panel data if you have it when you're doing unit-root testing. It's also been known how to make good use of covariates if you have them when you do unit-root testing. But it turns out that the cumulative effect of having both is, in a certain sense, bigger than the sum of its parts. So this super additivity, if you will, is something that had gone unnoticed prior to this article. So that's obviously of theoretical interest, and thankfully, it also translates directly into properties that will appeal to practitioners. And the article goes out of its way to explain exactly how to extract these efficiency gains that have been left on the table in the earlier literature. So, as I mentioned earlier, this is joint work between Arturas and Joachim Westerlund. But only Arturas is within 5 years of getting his doctorate, so he will be receiving the prize on his own. So congratulations, Arturas. So finally, before handing it back to Jaap, I'd say that my understanding is that unfortunately we don't have time for acceptance speeches or even an on-stage appearance because there is no stage. But at least I thought we could give a big virtual round of applause to the winners while we're waiting for Jaap to introduce the Sargan lecturer, Guido Imbens.
Yeah, thanks a lot, Michael. And of course, I add my congratulations to both the winning set of authors. I've been so fortunate that I could actually hand out a certificate to Arturas last week because he happens to live in Amsterdam, just like me. And so even though we don't work in the same place, I did manage to meet him, even though it's Corona times. So congratulations. On to the Sargan lecture. I'm obviously very excited that Guido Imbens has agreed to deliver it this year. As you may know, Guido is the applied econometrics professor and professor of economics at the Stanford Graduate School of Business. He's also currently serving the profession as the editor of Econometrica, which is much appreciated. I guess Guido needs little introduction. I guess neither econometricians nor empirical economists will need an introduction to his work. His early and seminal work on nonparametric IV estimation of heterogeneous treatment effects, and in particular of local average treatment effects, has had a major impact on both econometrics and empirical economics, and is routinely taught and applied by all of us, I guess. Guido has followed up over the course of the years with many influential contributions to causal inference and the econometrics of treatment effects and also other things. And in recent years, he has shed some brilliant light on important current topics like inference on treatment effects on subjects interacting over networks, and the use of machine learning to analyze treatment effect heterogeneity. Now, in the interest of time, I will just stop there and say that it's a great honor to welcome Guido, who's brought so much to econometrics and empirical economics, to deliver his Sargan lecture on causal panel data models. I must say the lecture itself is pre-recorded, but Guido is with us right now and here, and he will be taking questions. The questions will be moderated by Tobias Klein through the Q&A facility that's on the platform. Please submit your questions. We will get to them at the end of the lecture. And if you want, you can also vote on other people's or your own questions, and we can see which ones are the most urgent. And so please do submit questions through the Q&A, and let's all enjoy Guido's lecture now. Thank you.
Thanks very much for inviting me to give the Sargan lecture here at the Royal Economic Society meetings. I'm sorry I cannot be there in person. I would have loved to have been there. I first got exposed to Sargan's work when I was a master's student in England, in Hull. I've been reading and learning from his work for many years since. So what I want to talk about today is the recent, sort of fairly recent, very active literature on causal panel data models. You know, they really do two things. I want to talk a little bit about the general literature and kind of how I see the organizing principles, what is new in this literature, and what people are working on here. And then I want to talk about some specific results from my own work. And so, first of all, I should acknowledge this is based on the joint work with Dmitry Archangelski, Susan Athey, Motion Bayati, Leah Bodmer, Nick Duchenko, Skip Hirschberg, Kash Khosravi, Lua Lee, Xiaoman Luo, Jan Spies, Stefan Wager, Vera Warnick, and Ruslan Xian. There's a number of papers that kind of feature in parts of this talk. I'm obviously not going to go through all of these papers, but there's some common themes in some of this work. As a kind of general, I'm going to look at a setting where we have panel data, and we're going to be interested in the causal effect of a binary treatment. This doesn't actually necessarily limit itself to binary treatments, but there's a lot of special things there. I'm going to focus on that case because it's also much simpler. We're going to look at a setting where we observe multiple units. These units can be individuals, often more aggregate units, states, countries, or firms. We're going to observe these units repeatedly over time. It could be days, could be weeks, could be years. And so the basic outcome is YIT, where I is indexed by well, I runs from 1 to n, and t runs from 1 to t. So it's going to be a balanced panel. And we look at some cases where n may be much bigger than t and maybe much smaller than t, or they could be similar size. And the treatment may vary both over time and across units. We're going to look at a lot of special structures having to do with the treatment. Of course, there's a huge amount of empirical work in this area. I'm not going to list this, but in some of the earlier methodological work, people kind of describe the empirical literature in more detail. In particular, the recent paper by Janet Curry, Henry Clavin, and Esme Zvias kind of describes how the methodologies in this literature have become very popular over the last 20 years. And so in the general setup, I'm going to consider we observe that it's kind of separate from covariance, and I'm not really going to talk much about additional covariance here, but in many cases we can bring them in without changing the essence of the type of results we're talking about here. But so absent these covariates, we have two sets of variables. We have a matrix of outcomes, this n by t matrix, where the rows of this matrix correspond to the units, and the columns correspond to the time periods, and then we have a matrix of binary treatment assignments denoted by W. For the time being, and sort of for this talk, I'm going to assume there's no dynamic treatment effect. This is kind of, there's an older literature looking at dynamic effect, and there's some recent work, including this paper by Bojanov, Rambachan, and Shepard, where people actually bring in some of these dynamic effects. But here I'm going to focus on the setting where the outcomes only depend on the contemporaneous treatment, not on future or past treatments. Now, that doesn't mean I'm going to restrict the temporal correlation in the outcomes. We're going to allow for that in great generality. But the treatment effects themselves, the things we're interested in, are instantaneous. And it means we can think about there being two potential outcomes for each unit time period, y0 and y1, corresponding to whether the unit I in period t is being in the treatment group or in the control group. So what we observe is going to be this matrix of outcomes where the outcome corresponds to the realized value, either yit0 if the unit is in the control group in that period, or yit1 if the unit is in the treatment group in that period. And so we can also put this in terms of the potential outcome matrices. We have these two matrices y0, y1, where each entry in that matrix is either observed if the unit in that time period is in the corresponding treatment group, or not if it's in the other treatment group. So here, for example, unit 1 in period 1 is in the treatment group, so we don't observe y0, but we do observe y1. So for every missing entry here, there's a corresponding observed entry there, and the other way around. And so what we're going to be looking at, what we're going to be interested in the estimand is some average effect. And so here looking at the average effect for the treated. And that has the nice feature that we actually see all the things we need to see from the Y1 matrix, and it's just the missing entries in the Y0 matrix that are a problem. And so what we're doing either explicitly, some of the methods do this explicitly, or implicitly, is imputing these missing Y0 values. And so for this particular estimand, for the average effect for the treated, what we need is to impute all these missing values here using these observed values. We see the Y1s that we need, and then we can average the difference over the number of treated units. And so what we're doing is building statistical models, making assumptions that allow us to fill in these missing values. And now the first thing I want to do is kind of put some structure on that problem and kind of look at different cases. And there's two particular organizing principles I want to use here. First one is I want to think about the shape of these matrices. And this is something that came up in the earlier panel data literature as well, where often people looked at large N asymptotics, but sometimes also looked at large N large T or large T asymptotics. And so what I want to kind of distinguish here, of course, where exactly the boundaries of these classifications are isn't clear, but I want to keep these things in mind because some of the methods may be great in principle, but it may not work for particular configurations of the data. So you can think about three general cases. One where N is approximately equal to T, so where we have an approximately square matrix of outcomes. With here, I'm just writing down the Y0s where we have some missing entries there that we're trying to impute. We could also have the case where N is bigger, possibly much bigger than T. And so where the matrix has many rows but few columns. I'm referring to that here as the tall case. And then the opposite, where T is much bigger, or at least bigger than N, I'm going to refer to that as the fat case, where we have T relatively large, but relatively few cross-sectional units. And so this is in some sense kind of the trickiest case, but we see this fairly often when we use state data. We may have observation on 50 states in the US, and we may observe outcomes for 40 or 50 periods, and I'm going to look at an example of that type later. Or these could be countries, and we may have 30 countries over 20 years or 40 years. So these all fit into these settings where N and T are roughly the same size. At least we can't simply ignore the fact that one of them, that not both of them are very, very large. Now, that's kind of one organizing principle here, and I'm going to kind of keep coming back to that for particular analysis and particular methods. There's another way we can organize the problems in this literature, and that's kind of a much more recent thing. The earlier literature didn't really pay much attention to the possible patterns in the values of the covariates or the predictors. But so here I want to think about that more systematically. Because in the general case, there could be arbitrary patterns of missing data in the Y0 matrix, arbitrary patterns of assignment to the treatment. So here, unit 1, the first row of that matrix, is in the treatment group in periods 1 and 2, then in the control group for 2 periods, and later again in the treatment group. Unit 2 is in the control group the first 2 periods, then in the treatment group, then again in the control group. And so there could be a very general pattern there. That's actually not all that common. A much bigger part of the literature has very specific structures on the assignment process. Again, so here I'm giving the Y0 matrix, but the question marks correspond to W being equal to 1, and the check marks correspond to W, the particular entry in the W matrix, equal to 0. And so much more common pattern, and that's one that is explicitly the subject of much of this recent literature, is the staggered adoption case, where the units, once they get moved from the control group to the treatment group, stay in the treatment group forever. An example, sort of early example, that's a paper by Susan Athey and Scott Stern, where they look at adoption of enhanced 911 technology in counties in Pennsylvania. So the units are counties. Some counties adopt this technology early, some later, some never, but you never see counties initially adopting the technology and then dropping it again. Now, so this is a very important special pattern of treatment assignment, and there's actually a couple of special cases of that staggered adoption that I'm going to look at in even more detail. One of them is the case where only in the last period units are treated, and only some of them. So here, only these units and time periods are treated. Everything else is in the control group. I'm going to refer to that as last period assignment. Another setting is where there's one or possibly a few units treated over a number of periods, but all the other units and time periods are in the control group. Another special case of staggered adoption is what I'm referring here to as block assignment, where there's a group of units all switching to the treatment group in the same period of time, and everybody else in the control group. And then kind of the most special case, which is in fact a special case kind of all of the others, is where there's just a single unit period pair treated, namely one particular unit in the last period, and everything else is in every other pair is in the control group. And so these patterns are important because they're going to limit our ability to use particular methods, and they also suggest looking for particular patterns in the data to do the imputation. And so the recent literature has found it very helpful to kind of to pay explicit attention to the fact that the assignment is staggered rather than general and switches back and forth. And so next, what I want to do is just look at different parts of the literature that have focused on particular cases and kind of make people aware that in fact these literatures are really closely related and can all be thought of as fitting in this, looking at this type of panel data, but in particular settings. So the first case is kind of ignorable treatment assignment or unconfoundedness, where we look at typically at settings where we have a relatively large number of units, relatively few time periods, and only in the last period are some of the units assigned to the treatment. So the canonical application is a paper by Lalonde in 1986, where he looks at the effect of a job training program. And we have the outcome of interest is earnings. We observe earnings for 3 periods, one post-treatment to pre-treatment, and we observe the outcomes for a large number of treated units and a large number of control units. And so in that case, what people often do, kind of one of the most common methods, is kind of using matching type method. This may be kind of using inverse propensity score weighting. Nowadays, there's a lot of work on double robust methods, where we're somehow adjusting for these lagged outcomes as well as possibly other covariates, and then using that to compare treated and control units. And I want to look at a kind of a very parametric way of analyzing those data, not one that's kind of among the more fancier modern methods, but one that's going to make it easier to relate what this literature does to some of the other literatures dealing with this type of panel data. And so this very simple approach is just to do a regression using the control observations, estimating a regression of the outcome in this last period where some of the units are treated on all the legs, and then using that to impute the missing potential outcomes, missing control outcomes for the treated units, and averaging that over all the treated units. And kind of what is important here is that when we do that regression, the number of observations in that regression is the number of control units. I'm denoting that by n sub c. And the number of regressors is the number of lagged outcomes t minus 1 plus an intercept. So we have t regressors in total. And so that kind of shows that this is going to work better when n is relatively large. So we have a lot of observations, in particular we need n not to be relatively large, but we have a lot of observations, and t needs to be relatively small so we don't have too many regressors. It's not going to work so well if t is very big relative to n, because now we're doing a regression with lots and lots of regressors but very few observations. And we can still do that, and well, in fact later we will do that. It's not going to work so well. You would need to use regularization, kind of lasso-ridge type regularization to make that work. But in principle, what this unconfoundedness type regression is doing is looking for patterns across the time periods that are stable across all the units. And that's kind of the only thing it's doing. It's kind of treating the rows of this matrix as units of observation and assuming that the patterns there, the correlation patterns there, are the same for the control units as they are for the treated units. And that's kind of a key thing to keep in mind here. Now, an alternative is synthetic control type methods. Those are often used in settings where we have one or very, very few treated units. They're treated for a number of periods, and often in settings where we have a relatively large number of time periods. That's going to become a really big literature since the early work by Alberto Abadi and co-authors in the early 2000s. There's the Abadi and Gardia-Zabal paper, and then later the Abadi, Diamond, Heimüller papers. And so I'm writing it here in a slightly different way. You can see that in some of the work I did with Duchenko. You can think of the synthetic control estimators as based on a regression where now we don't take the last period outcomes as the outcome in the regression, but we take the outcomes for the treated unit, unit n, in earlier periods, in pre-treatment periods as the outcome. We regress it on an intercept and outcomes for the control units in the same period. So in this case, we take these data to run the regression. We take the columns here as the units of observation, and we're regressing the outcome for unit n on the outcomes for the other units. And so, kind of, if you do the counting, we now have t number of pre-period observations as the number of observations in that regression, and n is the number of regressors there. So again, this is not going to work. So in contrast to the unconfoundedness regression, they really liked the idea of having, where it was really helpful to have n much bigger than t. This is going to work much better if t is much bigger than n. And so given these estimates, then we use that to impute the missing values for the treated unit. And so what the synthetic control approach is relying on is that there's a stable relationship between this treated unit, in one of the canonical examples where the Abadi, Diamond, and Heimüller look at the effect of his anti-smoking program in California. They're looking at the relationship between California and all the other states, and they're assuming that that is stable over time. So it looks at a very different pattern in the data. It looks at very different dependency structures than the unconfoundedness regression, even though kind of in principle the data configurations are not necessarily that dissimilar. So again, if in fact n is really big, this is unlikely to work well, though you could formally still make it work by doing some regularization using, and the way I'm going to illustrate this later, I'm going to use elastic net regularization, but you can use any type of regularization to still get estimates. But if you rely too much on regularization, the results are not going to be very good, and it just doesn't work very well if t is small relative to n. Now, third special case where there's a big literature, it's kind of a more in settings where both n and t are similar size, but there's a block of treated units, and a very popular method there is difference. And difference is a two-way fixed effect regression, where you essentially estimate the treatment effect by running a regression of the outcome using all the data as outcomes, running the regression on a unit fixed effect, a time fixed effect, and the treatment indicator. Now, let me make some general comments kind of on this literature, kind of, and in particular kind of on the modern part of this literature. Given sort of this classification I've given kind of with these shapes of the matrices and the assignment patterns, there's clearly a lot of combinations that have received very little attention relative to these three cases where there's a very big literature. And there clearly is much more work to be done kind of in understanding what are effective methods for these other cases. Now, another theme that has received a lot of attention recently is that two-way fixed effects, which kind of often was used in this block assignment case. The two-way fixed effect doesn't work particularly well outside of that block assignment case, in particular if there's heterogeneity in the treatment effects. And a big theme of kind of the modern program evaluation literature is that we typically think that there is a lot of heterogeneity, and then we want to account for that and allow for that possibility. And I'll come back to this particular issue in a minute, but there's kind of there's a whole flurry of recent papers that look at different aspects of this and make different suggestions. There's also concern kind of by doing inference, in particular in cases where both n and t are not too large. Here are some of the papers, but there's much more work to be done there too. And that's obviously a very challenging thing when if one of the n or t is small and the other one is very large. It's kind of very natural to see how you would do inference, what type of asymptotics might work well. But in these cases where both n and t are relatively modest, that's not going to work so well. Fourth thing is that that in practice, it's likely that there's both correlation patterns over time that are stable across all units, which is kind of what the horizontal regression tries to exploit, but also correlation patterns across units that are stable over time, which is what the vertical synthetic control regression tries to exploit. And doing either horizontal or vertical regression, in some senses, kind of cannot be the right thing, because they can only exploit one of these correlation patterns, and it's likely that both are present. Now, if t is very small relative to n, there may not be much information in one of these patterns, and you may be able to ignore that. But in these cases where n and t are both modest size or similar size, it is likely that both these correlation patterns are there and are important, and that they should be taken into account. Fifth thing is that even though two-way fixed effect methods have gotten a lot of bad press recently, it is a very attractive model for starting to think about the baseline control outcome, especially when n and t are fairly small. It may not be flexible enough when we have enough data, when both n and t are bigger, but it's a very natural starting point, because the unit fixed effects tend to soak up a lot of variation. They explain a lot of the variation in outcomes, and the same with time effects. Now, first, let me come back to the problems with two-way fixed effect in the general assignment case. So if we have a block assignment case, you can write the two-way fixed effect estimator just as a difference in difference estimator. You average the outcomes for the post the treatment periods for the treated units, subtract the average outcomes for the pre-treatment periods for the treated units, and subtract the same difference for the controls. And that's all good and well. And in particular, the weights for the outcomes for the treated units are all the same. They're all positive, and the outcomes for and so it's all great. But what has been pointed out in this literature, kind of in different versions, if we have, say, staggered adoption or kind of more general assignment patterns, you can write the two-way fixed effect estimator. You can characterize that as a weighted average of the treated outcomes minus a weighted average for the control outcomes. But it turns out that these weights for the treated units, that those weights are not necessarily non-negative. They can actually be negative. And that doesn't really make a lot of sense, because you would think that if the outcome for a treated unit increases, that should be increasing our estimated treatment effect rather than decreasing it. But if that weight is negative, it means that if the outcome for a treated unit was increased by some constant, that would actually lower your estimate of the treatment effect. That doesn't really sit very well, and so people have kind of looked at lots of methods for trying to address that. And kind of one simple thing you can do there is say, well, let's estimate this two-way fixed effect model only using the control units. And once we have the fixed effects there, we can then impute the y0s for the treated units and average the difference relative to their treated outcomes. And now it's guaranteed that these weights for the treated units are non-negative, and we don't have that some of those problems. And we can still exploit the fact that these two-way fixed effects models do actually explain a lot of the variation. That is, in fact, a very reasonable starting working model in these settings. Now, for the rest of the talk, I want to kind of give some more specific new results. I want to actually talk about 4 themes here. Obviously, counting is not my strong suit. First, I want to talk a little bit about using more flexible outcome models than two-way fixed effects. As I said before, that two-way fixed effect may be a very reasonable starting model in settings where T and N are relatively small. But if T and N are bigger, we should do better. And I want to talk about how we can extend these models, what are natural ways of doing that. Second, instead of making that model richer, I want to think about estimating it only locally. Instead of estimating a model, a two-way fixed effect model to predict what's happening in California, using all the other 50 states, I want to estimate a fixed effect model, but only use states that are somewhat similar to California. And just like kernel weighting, I'm going to use some of the ideas from the synthetic control literature to estimate the two-way fixed effect model locally. And that's going to allow us to build a very tight connection between synthetic control and difference in differences methods that have often been viewed as quite distinct and where there's sort of a discrete choice to be made. Third, and fourth is quite closely related to that, which is why I originally had 3 themes here rather than 4. I want to look at design-based approaches where we explicitly model the assignment mechanism. In the cross-section program evaluation literature, there's a huge amount of attention paid to the assignment mechanism and to building models for the assignment mechanism, which is in that case the propensity score. And so we can do that here as well, and that allows us to build more robust methods that in combination with two-way fixed effect models or more general models allow us to rely less on the correct specification of the outcome model or on the correct specification of the assignment model, but rely on having both of these models provide reasonable working approximations. And last thing is this kind of emerging literature on actually doing experimental design type issues and looking at experimental design in these panel data settings. And that looks like a very promising literature with interesting early results. So now let me first start kind of with building more flexible models. And so a very natural way to extend the two-way fixed effect models is to model the control outcome as the low rank factor model. Now, we can sort of, if saying that this is a low rank model is not enough, we need to actually operationalize this. If we don't impose any restrictions here, we don't really need the error component. We can always write y0 as a low rank matrix. But what we're going to do is estimate a model where we shrink things towards a more low rank matrix, and that'll turn out to be very effective in getting a good model that allows us to be, is more general than a fixed effect model, but it still can be estimated well enough. So we rely on the fact that you can do the singular value decomposition where the eigenvalues of this diagonal matrix are the singular values of the low rank matrix L. We're going to estimate that, and now here there's some subtleties in there. We're going to estimate that using only the control units, and we're going to approximate y by three components: a unit fixed effect, a time fixed effect, and this low rank component. That is not identified. We can fit this just with L, because you can absorb the alpha I and beta t into the low rank matrix. But the key is that we regularize L by using this nuclear norm that penalizes the sum of the singular values, where we choose the penalty term lambda L through cross-validation. So we're pushing things a little bit towards a low-rank matrix. We're allowing the fixed effects, the unit and time fixed effects, to be unrestricted. And this gives us a very flexible approximation to whatever the Y0 matrix is. A very flexible approximation that as n and t get large will become more and more flexible, as opposed to a fixed effect model where the approximation may still be maybe arbitrarily bad when n and t is large. And so the result of this is a low rank matrix, kind of where the rank, so in principle here the rank could be equal to a minimum of n and t, but in practice with the regularization you end up with a very small rank, often 5 or 6 as the optimal rank given the cross-validation. Now let me show how this works and kind of put what the type of things we're interested in. So here we took data on daily stock returns for kind of a large number of stocks for a large number of days. And we created a whole bunch of subsamples there of size n times t equal to 4900, where sometimes we had few stocks but for a lot of days. Sometimes we had 70 stocks 70 days, and sometimes we had many stocks but few days. So we had these fat matrices, square and tall. And so if you look at this case, kind of where you have very few stocks, so here only 4, in fact this is smaller than what we use, but so say 10 stocks and a lot of time periods, in that case it's going to work very well to estimate the relationship between these last 2 stocks and the earlier stocks, because you have a lot of time periods to estimate that well. This so you would expect vertical regression, synthetic control regression, to do well here. On the other hand, you would expect unconfoundedness to not work well, because we can't, with just 4 stocks and only 2 in the control group, we can't estimate the relationship between the post-treatment outcomes and the hundreds of pre-treatment outcomes. We're trying to do a regression with very few observations and many, many predictors. So you would think that horizontal kind of unconfoundedness regression doesn't work very well here. The opposite case, if we have a very tall matrix, there synthetic control or vertical regression is not going to work, but unconfoundedness or horizontal regression is going to work well. You would expect that when the matrix is more square, that the matrix completion that is looking at both will do better. And so what we find is that, as expected, when the number of pre-treatment periods is much larger than the number of the control units, synthetic control vertical regression does much better than horizontal regression. When it's the other way around, and the number of control units is much bigger than the number of pre-treatment periods, horizontal regression does much better, or confoundedness does much better than vertical regression or synthetic control regression. But what is interesting is that the matrix completion estimator does pretty much uniformly better than either horizontal or vertical regression, and it adapts very well to the shape of the matrix. So here you can see that where the red line is the average root mean squared error for the matrix completion estimator, the neon green line is the vertical synthetic control regression that does very poorly when n is big, but it does quite well when n is small and t is big. And the horizontal regression does really poorly when n is small and t is big, but it does well when n is big and t is small. But the matrix completion kind of just adapts and does as well as the best of the other two everywhere. And kind of what's also interesting is to see what the rank is that we end up with. And so that the rank kind of, even though in principle could be as big as 50 or 60, is in fact typically quite small, but substantially larger than what we typically see in people using empirical work. So here, kind of message is that the empirical, the matrix completion estimate actually does quite well. Now, let me kind of move on to the local two-way fixed effect estimation. I'm going to make two observations first. One is that the synthetic control estimator can be thought of as doing a least squares regression with time fixed effects and unit weights, but no unit fixed effect and no time weights. And kind of when you look at this regression, it is a little funny. When we have panel data, we almost always put in a unit fixed effect because we know that explains a lot of the variation in the outcomes. Second observation is if you look at two-way fixed effect, that does have the unit fixed effects, it has the time fixed effects, but it has no weights. And you would think that by actually only using units that are somewhat more similar to the treated unit, you may actually do better than doing an unweighted regression. When we're trying to predict things for California, it may not help us very much to use Delaware or Arkansas as a comparison. We want to use states that are somewhat similar to California. And so synthetic difference in differences kind of combines these two ideas. It uses the two-way fixed effect specification with the unit fixed effects, but it includes unit weights and it also includes time weights. And so you can think of this as doing a two-way fixed effect model, but estimating it only locally, only using units and time periods that are similar to the target unit and time periods where we're trying to impute things. So here it kind of describes how the time weights are calculated, but it's just exactly the same as the unit weights. Now let me show how that works kind of relative to synthetic control difference and differences as well as relative to the matrix completion estimator. So we took this data from the CPS, essentially the same data that Bertrand Duflo-Malinathan used. Then we're going to simulate data from a model that has this low rank component, has a fixed effect component, has a zero treatment effect, and has normal errors. We're going to choose this low rank matrix of rank 2 and a fixed effect matrix as well as the variance covariance matrix of the errors to fit the CPS data. So the way we did that was first we estimated a rank 4 model, then we extracted the fixed effects from there, and use the remainder as the low rank component. So this is still typically a rank 4 component. But now we have a very general data generating process, and we can kind of switch off these fixed effects and the low rank component to see how well these estimators do in particular settings. And the final part, we kind of create this artificial treatment that depends on the low rank component as well as the fixed effects to not have it be completely random. And we'll see that that is actually important. So here we did a whole bunch of simulations for this. I'm going to just highlight a couple of things. One is kind of in the baseline case, if you look at the root mean squared error, the synthetic difference in differences estimator does much better than all the others. It's substantially better than the matrix completion estimator, which comes in second. It does a lot better than synthetic control of difference in differences. Where does it come from? It comes from having both the low rank component and the fixed effect. If we take out the fixed effect, then synthetic control does better. Not by much, but it does better. If we take out the low rank component, the fixed effect estimator does better. Not by much, but it does a bit better. It's also important that the treatment was systematically related to the systematic component in the outcome. When we use a random assignment for the treatment, we see that the synthetic difference in differences still does better, but not nearly as much as it did in the baseline case. And so in the paper, we have a lot more cases, a lot more details. We try different treatments generated in different ways, but the systematic finding is that the synthetic difference in differences estimator does very well in terms of the root mean squared error. And that comes from the fact that in many of these data sets, both these fixed effects and the low rank component are actually present. Okay, let me then switch to the final part of this talk. I'll talk a little bit about design-based methods and trying to bring in some of the the insights from design-based methods from the cross-section program evaluation literature. So here I'm going to think about a setting where we don't necessarily have staggered adoption, but where we have a substantial amount of variation in the assignment. So unlike the synthetic control setting that is often motivated by the case where there's just a single treated unit, so we can't really estimate assignment probabilities, here I want to think of multiple units being treated so that we can estimate some assignment process. But I want to allow in principle for a lot of non-linearity. So if we think about this as the potential outcomes have this unit-specific component, time-specific component, and a noise component, the problem is that both the treatment and the potential outcomes are related, are correlated with this unit-specific component alpha I. If we actually observe that, we would be done. We could just condition on that, and a condition on that we would have unconfoundedness, and we could adjust for these differences, and we'd all be done. Now, how does two-way fixed effect? How does the two-way fixed effect approach deal with that? Well, it puts a very specific structure on the relationship between the outcomes and the unit fixed effect. It assumes that a relationship is additive, and so we can just get rid of it. We can remove the dependence of the outcome on alpha without worrying about the treatment, without worrying about what the relationship is between the treatment and this unobserved component. But an alternative would be to try to take account, to try directly work with, to try directly model the relationship between the treatment and the unobserved component. And so to start with that, note that just by simple omitted variable bias formulas, you can see that you could get the fixed effect estimates by just running a regression of y on the treatment, adjusting for the average treatment for unit I and the average treatment for period t. But once you look at this regression, that suggests that we may want to adjust for these variables in more flexible ways rather than just additively. Now, at that point, you're kind of getting away from the two-way fixed effect approach, and it's useful to kind of think more abstractly about what we're doing in that case. And kind of the general thing, and this is also something that as precursors in the work by Altonji and Matskin, we can think about there being some statistic, some sufficient statistic S, such that conditional on that statistic, the treatment assignment is independent of the unit fixed effect alpha I. If we have such a sufficient statistic, then we would have unconfoundedness conditional on S, and we could simply adjust for differences in S to remove biases from comparing treated and control unit time period pairs. And kind of based on the earlier argument, what would be natural is to start by looking at the sufficient statistics that are things like the fraction of treated periods for a unit, or the fraction of changes in treatment status, and possibly the initial and last period assignment. And so there's some economic models, some of the structural models that have been used in this literature actually imply that this type of statistic has the sufficient statistic property that it removes the endogeneity of the treatment, and that therefore it's sufficient for removing biases in treatment control comparisons. Now, how do we exploit that? Given that we have this sufficient statistic S, we can look for estimators that are linear combinations of the outcomes, and we're going to put restrictions on these gamma, on these weights gamma, such that we're estimating an average causal effect with non-negative weights. And if the outcome model is correct, if the outcome model satisfies a two-way fixed effect specification, that gives us a bunch of restrictions that the gammas would need to satisfy to be consistent under that outcome model. If, on the other hand, I give you a sufficient statistic, that implies a different set of restrictions on gamma to make that work. If I give you a particular sufficient statistic, that implies that gamma should satisfy a set of restrictions in order for this estimator to estimate a meaningful average causal effect. And now what we can do, given that if we have not complete faith, but a little bit of faith, both in the outcome model and the assignment model, we could look for weights that are justified under the two-way fixed effect estimate model, and that are justified under the assignment model. And if we use weights that are justified under both, then we end up with a double robust estimator that's going to be more robust to misspecifications of either, because it doesn't rely quite as much on the outcome model as the two-way fixed effect estimator, and it doesn't rely quite as much on the assignment model as an estimator that only uses those restrictions. And so it's going to give us a way of getting more robustness by thinking about the assignment model in addition to thinking about the outcome model. Now, there's another way kind of thinking about this. And so this goes back kind of much more directly to the program evaluation literature. Suppose we just do a regression of the outcomes on the treatment indicator. Even if this model is not correct, if we use a weighted version of that, where we weight by the inverse of the generalized propensity score, then we're still good. We don't have to worry at all about whether the outcome model has unit fixed effects or has other functional forms in there. It's all good once you use the proper weights. But that's kind of somewhat of a knife-edge case. If instead of using this simple, this so simple model that's not very realistic, that's not very attractive, if you use something more realistic here, if you use a two-way fixed effect model, then these generalized propensity, inverse generalized propensity score weights don't work anymore. you need to adjust the weights to take into account the fact that you're using a more complicated model, because the two-way fixed effect model kind of uses future outcomes in principle to impute the missing potential outcomes in a way that invalidates the inverse propensity score weighting technology. So what do we do? How can we fix that? We want to look in a setting where we have an estimator for, or know from the beginning, what the generalized propensity score is. And we want to then look for an estimator, look for a set of weights lambda I, such that we get an estimator that is valid if the propensity score model is correct, but also valid if the propensity score model is not correct, but the two-way fixed effect model is correct. And so we want to look at this estimator, but then have weights that are a little bit more complex than the inverse propensity score weights, but they give us this double robustness. And it turns out what we need to do is we need to adjust these weights a little bit. We need to shift them a little bit with this denoted here by this capital pi of the assignment factor. And we can articulate conditions on those weights that tell us, that give us this double robustness. And it kind of it comes from the fact it's sort of specific to that that outcome model, that two-way fixed effect model, but you can derive what that condition is, and you can then get double robust estimators that are like the inverse propensity score double robustness in the standard program, in the cross-section program evaluation literature. Okay, so now let me end kind of by making a couple of comments on experimental design. So here, I want to look at one kind of just very specific question where there's a clear answer. Suppose we're actually doing a randomized experiment. So we have a number of units, probably not too many. But let's kind of think about the 50 states. Suppose we pick one at random to be treated, and all the other 49 are in the control group. We could then estimate the effect of the treatment by comparing the outcome for the treated unit and subtracting the average outcome for the 49 control units. That's unbiased for the effect of the treatment for that unit, and we know it has a lot of guarantees coming from the randomization. The question is whether it would make sense to use synthetic control estimators, which would essentially say, let's look, instead of looking at the average for all the other 49 states, let's just look at a weighted average of these 49 states, so that these 49 states look more like the treated state. It turns out that has kind of some major advantages, but it has some awkward features. One is, it turns out it does have considerably better root mean squared error properties. But it doesn't come with guarantees. It is in general biased. And it's kind of biased because units are not sort of over the randomization distribution. Units are not used equally often as controls. And that generates some bias. But then it turns out you can remove that bias by modifying the synthetic control estimate a little bit, by including additional restrictions on the weights that ensure that each unit will get used equally often as a control unit over the whole randomization distribution. And kind of to illustrate how that works, here we took the CPS data with 50 states, 40 years, outcome is average log wages by state and year. And we randomly kind of pretended each state in turn was being treated. We estimated the effect for that state, compared it to the actual outcome, so it should be close to zero. And then we looked at whether on average over all the 50 states, whether we were in fact getting zero, and what the root mean squared error was of that of the various estimators. What you see is that if you use the difference in means, you get a big fat zero for the bias. It is exactly unbiased. The root mean square error here in this case is 0.105. If you look at the synthetic control estimator, you do get a bias. It is not, and you can show this directly, you can in fact characterize the bias, it is not unbiased, but it does have much better root mean squared error. It has half the root mean squared error. You do much better doing a synthetic control estimator here, using a synthetic control estimator here, than a difference in mean estimator. But you do give something up. You potentially bring in bias, and that bias can actually be substantial. It isn't in this particular case, but you can make it essentially as large as you want. And so what you can do is kind of use this modification by restricting the weights, and it turns out that you can show that theoretically it removes all the bias is now exactly zero, but in fact it even improves the root mean squared error a little bit, though there the improvement is very modest. It's essentially the same root mean squared error as the synthetic control estimator, but it does maintain the guarantees that came from the random assignment. And so it suggests that in cases where we're doing randomized experiments with very few units, we may actually get substantial improvements if we use synthetic control type estimators to reduce the root mean squared error. And so what it relies on is kind of having these pre-treatment years. In this case, we couldn't stratify on these pre-treatment years because there's only a single treated state. So we're not changing the experiment we're doing, but we're changing the estimator in a way that leads to substantial, to arguably huge improvements in root mean square error. Finally, suppose this was a case where we actually used complete random assignment to decide which unit got treated. Now, suppose you could also go further and say, well, suppose we actually choose one of the states to be one or maybe two or maybe three states to be in the treatment group and all the other states are in the control group. How should we choose these treated states if we know we're going to be using a synthetic control type estimator? And now it's kind of tricky. It depends a lot on what the target is. If we want to get the average effect for the treated units only, we should choose units that are in the center of the convex hull. You want to choose units to be in the treatment group that are very average. You want to choose Kansas, because you can approximate Kansas by combination of all the other states. On the other hand, and if you get two states, choose Kansas and the next state over, because you want to get states that are very much in the center of the convex hull. On the other hand, if you want to estimate the average effect for all the units, you would like to choose states that span the whole space. So if I could choose 4 states, and I want Florida and Maine and Washington and California, so we span all possible states. We can estimate the effect for all the states in the middle, because it's easy to construct a convex combination of those 4 states and approximate any state in the middle, at least geographically, not necessarily by other characteristics, but if we think of this purely in geographic terms. So it depends a lot on what the target is. If you want to just get the average effect for the treated units, you want to choose units in the center of the convex hull. But if you want the average effect for all the units, you want to choose units that are far apart so that they span the convex hull. Finally, if you can actually design an experiment where we can choose which units are treated and also when they're treated, the problem becomes even more complex. You would, in principle, want to start with a few units treated and slowly increase the number of treated units in a staggered adoption case. And this type of experiments is actually getting some traction in some of the tech world. So let me stop here what I hope I've illustrated in this talk is that there's lots of new developments in the causal panel data literature that has greatly improved our understanding of the two-way fixed effect models, but it's also opened up lots of new directions for research where we can use design approaches to estimation, inference, and experimental design that gives us opportunities to find more robust estimators, but there's still a lot to be done. So I expect this area to continue to be very active for the foreseeable future. Thank you.
I'm sorry. Thanks a lot, Guido, for this nice presentation. So we move over to the Q&A. Guido is here, as I said, and Toby, there's some questions. There's still, if you hurry up, you can still ask some of your questions in the Q&A facility. But then I'll give the floor to Toby to moderate, because he's the moderator.
Exactly. Thank you very much. So at this point, we have 4 questions. I'm going to start with the question that received the most likes. So that question would be, do any of these approaches extend more or less readily to distributional treatment effects versus the average or ATT?
Thanks. Yes, I think we can also a lot of these insights extend fairly directly to looking at objects other than the average treatment effects. There's sort of very few functional form specific assumptions in here. The details would have to be worked out, and especially exploring the presence of heterogeneity in treatment effects would be very interesting, and not a huge amount of that has been done yet. So that would be a very fruitful area for the future research.
Excellent. Another question we received was, I would be interested to hear Guido's views on the main challenges and opportunities in moving to dynamic treatment effects, which seems a practically important extension.
Yes, that's clearly a hugely important area. And so the tricky thing there is that at the moment, these methods allow for a lot of heterogeneity in the treatment effects. And once you also have dynamic components to the treatment effects, you're going to have to somehow limit that, because it's unlikely that the data are going to be rich enough to allow kind of the very flexible estimation of dynamic treatment effect. So the challenge is going to be to build models that capture most of the likely patterns of dynamic treatment effects, kind of whether these effects are likely to slowly die out over time, or whether there's heterogeneity in them by calendar date. But that's again going to be a very interesting area to kind of, where the earlier literature kind of somewhat say the Abraham-Heckman chapter kind of has a lot of details on different versions of that, how that would mesh kind of with these more design-based approaches.
Mm-hmm. The third question would be, I was wondering, what is the key theoretical benefit of using synthetic differences and differences as compared to linear models with factors included directly in the regression equation? By factor, I mean nuclear norm regularized low rank component.
Yes, so there the insight kind of from the program evaluation literature is that there are substantial benefits to not just modeling the outcome process, kind of the conditional mean of the outcome given the covariates, but also modeling the assignment process. You get the double robustness, and kind of the recent work by Chernosikov and co-authors kind of has shown that in practice, you get much better finite sample properties exploiting both models for the outcome as well as models for the assignment mechanism. And so the nuclear norm, the kind of matrix completion methods focus solely on modeling the outcomes as a function of these latent factors. And the synthetic difference in differences combines building a model for the outcomes with doing things locally, which is essentially corresponding to modeling the assignment mechanism. And so by reducing the weight on units that are very different from the treated units, you're going to build in robustness, and it's likely that in practice, this is going to give you better finite sample properties in cases where the outcome process is difficult to model.
Thank you very much. I think we would leave it at that in the interest of time. And with this, I would like to hand back to the chair. Yeah.
Thank you, Toby. Thank you, Guido, for a great presentation. So, for sure, if anyone has any further questions for Guido, he will be happy to get your responses. I just want to close with a few comments about the program. Tomorrow, if you're interested in econometrics, and you may be if you're in this session, tomorrow at 12:15 British summertime, there's a informal get-together on Zoom that's now on the program. I'll be chairing it and drinking my coffee in it, but you can chat about whatever you want, broadly about econometrics. And the Econometrics Journal also organizes a special session on dynamic discrete choice analysis, which is at 3:30 British summertime. And that has presentations by Victor Aguirre-Gabiria and Martin Pesendorfer on various state-of-the-art topics in the analysis of dynamic discrete choice and games. So I hope to see you there. I would also like to point out on request of the organizers that you can provide feedback on the sessions and the conferences on the various buttons, feedback buttons on the left and right, and the organizers would really appreciate if you would do so. And so finally, thanks again to Guido for making time for this and having this session. This was great, and I think it's a great line of work, and I think we've all learned a lot. And so thanks a lot. And with that, I would like to close this session. Thank you.